So I think it's time to start. Welcome everybody to this afternoon session. My name is Patrizio Campisi. I am from the University of Rome 3 in Italy. And I have the privilege to chair this competition session here at ICB-2013. So we have 5 presentations. In the program, you will find just 4, but there is another one which will be added at the end of the 4 schedule. And so, we have one presentation that will deal with face recognition in mobile environment. The second one with speaker recognition in mobile environment. The third one will be on anti-spoofing, yes, for 2D images. And the fourth one will be on fingerprint liveness detection. And the fifth one will be on iris recognition, on spoofing for iris recognition. So we'll give the floor to Sébastien Marcel for giving a few words of introduction to this session, and then we can start with the presentation. Please.
Okay, thank you, Patrizio. So, good afternoon. So, welcome to this session. So, I'm Sébastien Marcel. I'm one of the competition organizer, I would say, for the series of competitions. But today we're going to listen to the people that were mainly active into the competitions themselves. So, just to give you a couple of figures, and then I will give the floor to them. So, originally we planned to 8 different competitions, ranging to face recognition, speaker recognition, and also liveness detection and to iris recognition. In the end, there was only 5 of those competitions with enough participants. So in the end, we just have 5 competitions for which we have effective, basically, results to be able to be shown. Again, finally, there will be 4 papers out of those 5 competitions, for which proceedings will be that will be in the proceedings. So you'll be able to find the details in the papers of what we see today. So just a bit of figures about the 5 different competitions that you will see in the next presentations. So for the face recognition competition in mobile environment, mobile database, there was 8 participants and with 8 submissions, means 8 systems submitted. For the speaker recognition, there was 11 participants with 12 systems, speaker recognition systems submitted for evaluation. For the competition on anti-spoofing, there was 8 participants and 8 submissions. And for the liveness, the fingerprint liveness detection, there was 9 participants and 11 systems. And finally, the iris competition, 8 participants with 13 submissions. So you can see that from those figures, those competitions have been quite successful with a significant number of participants and also systems that will be able to give maybe some directions for future research, or what works or what doesn't. Maybe open the floor also for discussion. So now I will close this my keynote, I would say. And I give the floor to the presenters. Anyone? Thank you.
Thank you, Marcel. I will present the first competition, which was the face recognition evaluation in mobile environment. And after I give a short motivation why we did this competition at all, I will shortly introduce the Mobio database and the participants and their algorithms, briefly discuss the results, and end with the discussion. There are, as we have heard in the morning, there are 3 different applications of face recognition. So the first one is the access control scenario, which is regularly tested by face recognition vendor tests by NIST. So there is no need to test this again. There is a second application, which is the forensics, but due to some legal reasons, there are no publicly available databases for forensic cases. And so we cannot test these, but there is the new upcoming application of face recognition, which is a private use. And for that we have collected a database with some challenging sorry. Okay, so the challenges are that they are uncontrolled illumination, the images as you can see there, and you have some facial pose included. Since this is a video database where people were talking, they might only be partially visible, and yeah, they have facial expressions due to the talk. The Mobio database is, as I said, a bimodal video database recorded from 50 female and 100 male clients. These videos were taken with mobile phones, and this database can be downloaded for free from our webpage. For the face recognition evaluation, we extracted one image from each video, and we hand-labeled the eye positions in these images. And gave the images and the hand-labeled eye positions to the participants, which then could use these images for their evaluation. And the database is partitioned in 3 different sets. So the clients are split between the training set, the development set, and the evaluation set. And there are 2 evaluation protocols depending on the gender. One is the male protocol, where only male clients are compared, and one is the female protocol, where only females are compared. To have an unbiased evaluation, we provided a strict evaluation protocol, where the images from the training set could be used to train the face recognition systems, and also to perform some score normalization. And the images from the development set are from different identities. And one particularity of the Mobio database is that a client model is enrolled from 5 images. So the participants had to come up with some idea how to integrate the information from 5 images into one client model. Afterwards, the remaining probe images from the clients are tested against all models, and these scores are used to evaluate, and also they can be used to train the score calibration system. Finally, there was the evaluation set, which was more or less the same as the development set, except that there were different clients, and the probe file names were anonymized, so that from the probe file names you could not guess the identity of the client. In total, we had 8 participants from 8 different countries, which successfully submitted the scores for both the development set and the evaluation set. And they also had to provide a system description, which I will just briefly introduce here. There was a baseline system that we provided as open source, which was a simple LDA based on gray values and compared with the cosine similarity function. There was the 4 simple systems and 4 fusion systems. The first simple system just used a local binary pattern histogram sequence and compared that with a chi-square distance measure. There was a convolutional neural network features. There's 2 participants, which enrolled a linear model after performing an LDA and used a dot product to compare these models. There was a F3 face recognition system from which extracted local Gabo binary pattern histogram sequences and enrolled the models with the least squares algorithm. We had one system which used the Gabo graphs with a Gabo face-based similarity measure and some local enrollment strategy. And there were, for the fusion systems, one histogram of Gabo face patterns and local phase quantization algorithms, which are compared with some histogram intersection measure. There was the F2 system, which fused pattern of oriented edge maps and Gabo jets with a correlation measure. there was the F3 system, which used 3 different types of local binary patterns and compared that with support vector machine and with some histogram averaging. And the most complex system probably was the F4 system, which used multi-representation PCA using 3 different image representations and extracting from these image representations features like local binary patterns, Gabo features, and also color information. And they used some temporal fusion to fuse these algorithms. The evaluation measure is based on the half-total error rate, or one of the evaluation measures. So to compute the half-total error rate on the development set, one needs to have a threshold, and this threshold is estimated on the evaluation set, on the development set, based on the equal error rate on the development set. And then the equal error rate and the half-total error rate are computed as the average of the fault acceptance rate and fault rejection rate of these 2 sets. And we also show receiver operating characteristics to see if different operating points give other results. And here are the results of the 8 participants plus the baseline. And they are split up into, again, the simple systems and the fusion systems. One can see that the male clients could be identified easier than the female clients, which corresponds to previous findings on this database, and that the equal error rate on the development set is usually lower than on the half-total error rate on the evaluation set. One can also see that mainly the results are comparable. So they, for example, for the male half-total error rate, they reach from 7.5% to 12.0%. So there's not much of a gap. So I would say all of these participants, all of these algorithms reach state-of-the-art performance. But still there are some algorithms which performed best. And from the simple systems, it's definitely the S2 system, which was the convolutional neural network, and the F4 system was the best score fusion system. What is also to be noted is that especially the F4 system has a very low recognition rate, low error rate on the development set, but they are comparable in the evaluation set. And we also show the ROC curves to see that, for example, in the female, which is on the left, the UniAlp system, the F4 system, performs best in most cases, but for very low fault acceptance rates, there is the EDAP system, which is comparable at least. And for higher fault acceptance rates, there are some other algorithms like the S2 system. And on the male evaluation set, so the results are similar. So that was already my part. What we have found is that in face recognition, there are several state-of-the-art features that are used. For example, Gabo features, especially since a couple of years, the Gabo phases gained some, are more important. Then there are the local binary patterns or local Gabo binary patterns. Color information is very useful, and also multiple representations. But the best feature that we have found in our competition was well learned with the convolutional neural network. And on top of these features, there are different state-of-the-art face recognition algorithms. The best one is clearly the multi-representation PCA, and also the linear discriminant analysis showed quite good performance. But and we had support vector machines, partial least squares algorithms. We had histogram sequences of various feature types, which seems to be very popular recently. And the score fusion was done with logistic regression, but as we could see, that this leads to quite some overfitting in the evaluation set. Thank you.
So let's open the floor for discussion. Any questions? Yes. Do we have a microphone? Do we have a microphone? No? Okay.
You presented the conversions in terms of accuracy, which would it be fair to include the time factor as well? For example,
Yes, we have done the time evaluation and also the memory evaluation in the paper, but they didn't make it into the talk.
Okay, so it's there.
It's there.
Yes. Any other question?
Thank you. The overall result is a list of half total error rates or equal error rates, which is fine. But I would like to foresee to learn more from these results, namely that on the feature level, what is the strength of each feature or weakness of this feature. This sort of studies wouldn't necessarily result in a full system, but rather to, for example, using a common classifier, but only varying the features. From this aggregated results, it gives a hint, but it doesn't necessarily give a full insight into the various strengths of
Yes, I totally agree.
subparts.
I totally agree. And but this evaluation was evaluating systems from different participants, so we could not even enforce these participants to use a specific type of features or a specific type of algorithms. But a study like that is definitely needed. That's true.
Okay, last question.
Have you considered performing statistical tests to see if the differences are statistically significant better?
Sorry, could you repeat that?
If you have performed statistical hypothesis tests to determine if a method is actually better than the others, or if it is something random?
Yes, no, we haven't done any statistical test. This is a fixed evaluation protocol that we fulfilled, so that really every participant could had to use the same data for identical steps. So there is no randomness in it.
Okay, very last question.
Yes, I just want to know if the database will be available to...
The database is online.
Okay, so let's thank the speaker. Okay, so we can move to the second presentation, the 2013 Speaker Recognition Evaluation in Mobile Environment, and the talk will be given by Elie Curie.
Thanks. Okay, thanks, Professor. So I will present the outcome of the competition we were organizing on speaker recognition using mobile environment and using the same database that was used for face, which is Movia database. So as for face, there is Movio has many challenges. First, there is real noise, there is acoustic distortion, there is distance between the speaker and the microphone, there is reverberation, and there is also short duration speech segments, which makes the main difference between Movio and NIST speaker recognition evaluation series. For example, in this histograms, we can see the distribution of the duration of speech segment on both Movio and NIST speaker recognition evaluation. And we can see that the average duration for speech segment for Movio is around 8 seconds. However, it's 11 times higher for NIST speaker recognition evaluation series in 2012. So at the beginning of the competition, we had around 20 registered participants, but only 12 of them were able to submit valid scores, so they submit 25 valid submission, and only 12 of them was considered as primary and official scores. Here we can see the list of this participant, their identifier, the institution that they came from, and the country. So in the next few slides, I will talk about the system description, briefly, of course, of those participants. But let's first present the general architecture of a speaker recognition system, which more is similar to face recognition. We have three main steps. The first one is feature extraction, where features are computed, denoised, and non-speech part are removed, which we call the voice activity detection. And also some feature post-processing is done, like warping, like normalization or other things. The second step is modeling, where people do, they model the background, and then in the second step they enroll the client-specific model. The third step is the scoring, where they estimate the likelihood between the trial and the model, the client-specific model. So that's the general architecture of a speaker recognition system that all the participants were doing. So, let's now go more in detail of what those participants were using. So first, for the feature extraction, they were using different kind of features like MFCC, LFCC, PLP, or F0, and the third formant. For voice activity detection, they were using different kind of features like energy, F0, which is the fundamental frequency, and the zero cross ratio, and also others were using 4 Hz modulation energy, or also the phoneme detection. For post-processing, they were using different kind of techniques like feature warping, Rasta, and, for example, the Capstral mean and variance normalization. And here is a summary table of what each of the participants were using. For example, you can see system 1, they were using 3 kind of features: MFCC, LFCC, PLP. For the energy, they were using for the voice activity detection, they were using only the energy, and the feature post-processing, they were using Capstral mean and variance normalization. However, we can see that, for example, system 11, they were using MFCC, only MFCC, but they were using more sophisticated voice activity detection. Mainly, they were using energy, F0, and phoneme to remove the non-speech part. And for feature post-processing, they were using feature warping. Okay, so that's at the feature extraction level. So as I said, the second step and the third step are the modeling and the scoring, but they are very related. So I mean, the scoring depends on the modeling techniques that were used. So for instance, I grouped the different participants into four big group. The first one, people were using, some participants were using the Gaussian mixture model, which was proposed in 2000, and the scoring was done using log likelihood ratio. The second group was using Gaussian supervector, and with NAP as session compensation and SVM for scoring. The third group was using intersession variability with linear scoring and ZT as score normalization. The majority of the participants were using total variability that was recently proposed in 2011, which is also known as I-vector. And so we have actually 7 participants that use total variability, but they were using different kind of post-processing and session compensation like LDA, length normalization, within class covariance normalization was presented by one of our colleagues, and the conformal in-bending analysis. For the scoring, they were using either PLDA or also cosine scoring, and for the scoring normalization, they were using linear calibration, length-dependent logistic regression, S-norm, or also T-norm. And then there is some of the participants were using kind of system fusion, and for this they were using, all of them, they were using logistic regression. Here is a summary table of what the participants were using. We can see, for example, system 2, TVS, they were using I-vector plus length normalization for the modeling, and then for the scoring and score normalization, they were using PLDA and S normalization. Whereas, for example, other systems like Min Telecom, they were using GMM and log likelihood ratio. Now let's talk a little bit about the results that the participants were getting, the official results. So first we evaluate also as presented by my colleague, we evaluated in terms of equal error rate and half total error rate. And this is a summary. This is a summary table of the results on both female and male. The star sign means that the participant were using a fusion system. The plus sign means that some system were using external data for background training. And so the best results are in red. We can see it's Alpinium system that we're using 9 subsystem. All of them based on total variability. And in the blue we have the best single system. We can see there is JAPSI, there is Min Telecom, and there is Phoenixia. And for example, JAPSI, they're using GMM, but with special gender-dependent features. Min Telecom were using some external data that is suitable to mobile devices, and Phoenixia was doing using total variability, and they were more or less over-tuning on the development set, as we see. Second, we evaluated in terms of detection error trade-off. Here the curves, if it's close to the origin 0, it means that it's better. So I'm not used to Windows, sorry. Okay, so here also we can see that the best system in red is also the Alpinium system, but there is some special cases. There is some operating points where Min Telecom system was outperforming the best system. And we can see that all the participants had a good calibrated system, because all of them had a dead curve that is more or less straight line, and the angle was close to 45 degrees. And finally, we did a last experiment. We took all the primary system of the participant, and we did kind of system fusion. And we were impressed by the results we got. We could also improve the results by more than 30% on both female and male. And so we think that there is still room of possible improvements of the single systems. Finally, so we evaluated 12 primary systems. The best system is based on total variability plus system fusion, and the fusion of all primary systems was also improving the results. And the future work will focus on bimodal fusion between face recognition and speaker recognition, and all the scores for both face recognition and speaker recognition are available. So people that would like to work on fusion on both multi-algorithm or multi-model fusion, they can just use those official results, or official scores. And finally, the evaluation, the system fusion and our system for both face and speaker system, they are done by using Bob, which is an open source toolbox for speech processing and machine learning, and that is also available on this web page. Thank you for your attention.
that the evaluation you presented is very interesting because it's a very specific scenario which is very challenging, which is a mobile environment. So I wonder if, as for the phase, is there any specific lesson that we can learn? Any lesson we can learn from your evaluation? Like any recipe would you leave or give to anybody who wants to develop a recognition system on a mobile environment?
Well, as it's seen in this conclusion that it looks like total variability is now becoming a state-of-the-art system for speaker recognition, and I think the new direction should also go through system fusion, which looks like very impressive, and there is a lot of complementary information from different systems, from different kind of features, from different kind of filter bank for a speaker. So and also the good thing that those systems are also were also tested for face recognition. I mean, total variability was also tested for face recognition on Movia database, and other kind of techniques that I presented, like GNM, like ISV. They were also presented on. They were also tested for face recognition on the same database, and we were getting state-of-the-art results, and maybe in some cases they were outperforming this thing. So that's I think total variability and system fusion is nowadays the direction that people should go, at least should take, at least in speaker, and there is a lot of work to do for session compensation and post processing of the iVector.
Thank you for your efforts with the competition and a wonderful presentation. I was wondering if you have fusion results using less systems. Instead of 12, let's say 2, 3, and the performance improvement obtained with less systems. My impression is that perhaps you may obtain also good performance improvement.
Yeah, I'm pretty sure about this, but we didn't want to go in detail in this. I mean, with different, with sorting the systems and taking maybe the N best as.
Did you already did this?
But I'm pretty sure we will get better results, because actually there's two of the systems were buggy, and even with this buggy results, we were the fusion technique that we used was able to outperform the best single system. So for sure, by taking less systems, we could get better results.
Any other questions from the audience? Okay, if not, let's thank the students again. Let's move to the third presentation, titled The Second Competition on Countermeasures on 2D Phase Spoofing Attacks. And the presentation will be given by Ivana Chinkowska.
Okay, so today I'm going to present the second competition on countermeasures to 2D phase spoofing attacks, which was organized by IDIAP Research Institute and took place at the beginning of this year. So in my talk, I'm going to introduce the problem of anti-spoofing first. I'm going to talk about the motivation for our competition, about the competition itself and the solutions that we received. And at the end, I'm going to discuss the results and the conclusions. So what is spoofing in face recognition in general, or in biometrics in general? It is also known as a presentation attack. It is a direct sensory attack to the system, where some user who is not registered to the system tries to access the system by presenting a copy of the biometric trait of otherwise valid user. For the face modality in particular, there are many ways how one can spoof a face. The most common ones are using a printed photograph, presenting a printed photograph in front of the recognition system, or a digital photograph displayed on a mobile device, then video playback, 2D or 3D face mask, and so on. And some of these types of attacks you can already see at the spoofing challenge. And we can actually expect that in future we will have even more advanced types of spoofing attacks. To spoof a face is particularly easy just because faces of people can be easily found on the internet, or they can be also taken cooperatively or at distance. In face anti-spoofing, recently many algorithms have been developed in the past years, let's say, but most of them can be categorized into three broad categories: texture-based, motion-based, and liveness-based. All of these categories are looking at the problem from different perspectives. The texture-based, for example, are trying to find some texture artifacts on the spoofing attacks. The motion-based are trying to find some unnatural movements, again, on the spoofing attacks. The liveness-based are examining some physiological activities which are typical for the real accesses, for example. So what is the motivation for organizing this competition? The first competition on countermeasures to 2D facial spoofing attacks was organized in 2011, but the algorithms were evaluated on the printed face spoofing database. This database contains only spoofing attacks with printed photographs. And in our case, we wanted to go one step further. So we had two goals in mind. The first one, we wanted to probe the current trends in face anti-spoofing. We wanted to see what researchers are working on at the moment, and we wanted to assemble a nice set of state-of-the-art methods in anti-spoofing. But even more important for us was to challenge them on a variety of spoofing attacks, on different types of spoofing attacks. So that is why we selected Replay Attack face spoofing database for evaluation of the methods. This database contains video files of real accesses and attacks to 50 different identities. There are three types of attacks. So attacks using printed photographs, photographs displayed on a digital device, and video playbacks. The samples in this database are recorded into controlled and adverse conditions. Then the spoofing attacks are recorded using fixed or hand support. Then there are also different photo qualities. For example, for the digital spoofing attacks, we were using mobile phone or iPad, for example. And all of these conditions actually introduce just another level of variability in the database. Furthermore, this database has an unbiased protocol with precisely defined train development and test set. And also it provides enrollment videos which can be used to train a face verification system and to assess what is the effectiveness of the spoofing attacks to bypass a face verification system. Here are some examples of the database, and the database, it can be downloaded from the link which is written there. So about the competition itself, the participating teams had a period of 3 months to develop their algorithms. During the course of the competition, they had access to the full database, so to 1,200 videos in the training, development, and test set. However, to ensure that we have a fair competition, we provided an anonymized test set, which is actually only clipped version of the videos from the original test set. These clipped videos contain 100 frames with a random starting frame from the original video. And we also provided automatic face detections for teams who actually want to perform the spoofing detection only from face bounding boxes. Here is a list of the participating teams. We have 8 participating teams from 11 different institutions and from 8 different countries. And in the next slides, I'm going just to briefly explain their solutions, but the details, more details you can find in the paper. So to start with the team from Cassia, they are looking at the problem from 2 different perspectives. So they are performing motion analysis in different regions of the image and also texture analysis. And at the end, they fuse the 2 types of features at feature level. The IGD team, they're using a computer vision technique for magnification of subtle changes which can happen in a video. And in this case, they're using that to magnify the changes that may happen on the face of a real access, let's say. And these changes are happening because of blood flow and because of the pulsation of the cardiovascular system of the humans. And this they're using as a cue for liveness for detecting real accesses. The mask down team creates a composite system by fusing different categories of countermeasures, in particular 3 categories: motion-based, texture-based, and dynamic texture. They are fusing them at score level, and one additional contribution of this team is that they provide the source code of their algorithm for easy reproduction of results. The 4th team, LNMIIT, they're again looking at the problem from 2 different perspectives. They're doing motion analysis and they're extracting also texture-based features, and then they're fusing them using feature-level fusion. The movies team are extracting only texture features, but 2 types of texture features, LBPs and Gabor wavelet transform, and again they're fusing them at feature level. The team from Pralab, they are also extracting features from single frames, so from static frames. So they extract texture features, but besides they're extracting color and edge features, and then they're using dynamic score combination in order to select the features that get best scores, and then they're assigning appropriate weights to all of them. The ATVS team assumes that the recaptured images or the spoofing attacks may have different quality than the original real accesses, and that's why they're extracting general image quality measures, both full reference and no reference image quality measures, and they're using these measures as a feature vector. And finally, the Unicamp team, they're extracting noise signature from the videos, and then they're performing spatiotemporal analysis on this noise signature, and using visual rhythm technique, they summarize the content of the video into a 2D image. So then in the evaluation phase, we asked the participants to provide the score files for the development and for the test set. We calculated the decision threshold using equal error rate criteria on the development set, and then we computed the half total error rate on the anonymized test set. And here are the results that we got from the 8 teams. The blue bins here represent the HTR on the development set, while the orange bins, the HTR on the anonymized test set. And as we can see, we have actually 2 teams which achieve perfect discrimination between the spoofing attacks and the real accesses, both on the development and on test set. Then we have 3 other teams which achieve very good performance, so from 0 to 0.5 half total error rate on the development set, and they're just slightly worse on the test set, but still the performance is quite good, from 1.25 to 2.5% HTR. So let's see if we can find some kind of patterns in the methodologies that the teams are using, so patterns that can lead to better results. For example, the 2 winning teams, Cassia and LNMIIT, the both of them are tackling the problem from 2 different perspectives. So they're doing texture analysis and motion analysis as well. Similar approach is taken by Mask Down team, while the other 2 very well performing teams, Movies and Pralab, they're extracting only texture features. With regards to the fusion techniques that they're using, the winning teams have this step in common as well. So they're using feature-level fusion for their texture and motion-based features. The Mask Down team, on the other hand, which performs slightly worse, they perform score-level fusion. Movies and Pralab also perform so feature-level or score-level fusion respectively, but they're using just one type of features, so texture-based features. And the rest of the teams, they don't perform fusion, except IGD. So from here, maybe we can already see that fusion in general, feature level and score level helps. So to conclude my talk, again, the goal of our competition was to probe current trends in face anti-spoofing, to see what are the new directions, and to do a fair evaluation and comparison on different methods on variety of attack types. We received 8 innovative anti-spoofing algorithms. Each of the teams contributed from in a different way. Some of them proposed novel approaches, some of them proposed even novel cues for spoofing detection in face recognition. And one trend that most of the teams are following in general was the trend for fusing different approaches. From the results, we can see that almost all of the teams outperform state-of-the-art, which has been previously published on replay attack, or at least they're comparable to the state-of-the-art. And as I already said, fusion in general, especially fusion of different types of countermeasures, helps and is very effective. And this conclusion is very important because in future we can expect different types of spoofing attacks to appear, and probably we will have to attack these different types of spoofing attacks in a different way. So in that sense, in order to be able to cope with many categories of spoofing attacks, probably fusion is one of the directions that we have to consider. About future challenges for competitions similar to ours. So first of all, replay attack database is a database which contains a variety of spoofing attacks, and it has a large variability. But still, we saw that the spoofing countermeasures at this point probably have the level of maturity that they can easily distinguish between the real accesses and the spoofing attacks in this database. So, important task for replay attack database, but also for other face spoofing databases, will be to enhance these databases with more challenging samples. We can do this in 2 ways in particular. First, we have to introduce more realistic spoofing attacks or more challenging spoofing attacks. And another way how we can do that is to introduce the variabilities which are typical for the face recognition databases into the spoofing databases. Like, for example, variabilities in the recording conditions, in the illumination conditions, the devices that are used, the pose of the person, and so on. Additional interesting experiment for some future competition would be also to see how the algorithms generalize when they're tested on a different database. So what will happen if the algorithm is trained on one database or on one type of attack and tested on a different database or a different type of attack. So thank you for your attention.
You already have a lot of materials for new challenges, right? So any question? Massimo.
Thank you very much. It was very interesting. The most intuitive way to discriminate a real face would be to use the 3D information to me. Is there any reason why nobody used this data? Because you can infer from motion, for example, or from shading.
Yes, well, I don't particularly know, but I guess that the equipment that you need for this type of experiments probably is not available in many institutions, and also or for example, to reconstruct the 3D structure from 2D images is also like a separate problem that probably these teams which are working in anti-spoofing are not familiar with. So I guess that might be the reason. But I believe that there are research teams that are working on this topic. And hopefully in future we have some solutions.
Any other questions? Yes.
The video that you in the database that used as a replay attack, was it held by hand or was it on a fixed thing?
So we have 2 types of attacks in the database. So the first type are videos which are recorded with a person holding the device by hand, and the other one in the other type, the device is just put on a fixed stall. So we have the two types of attacks in the database.
You have a question? No? Okay, so let's thank the speaker once again. Now let's move to fingerprint. So the fourth presentation will be Fingerprint Liveness Detection Competition 2013, a short live bet 2013, and the presentation will be given by Gianluca Marcialis.
Okay, good afternoon. On behalf of the organizing committee of the LiveDet 2013 Fingerprint Liveness Detection Competition, I will present to you the main results of this competition. This is the third edition of Fingerprint Liveness Detection Competition. The first one took place, hosted in Vietri sul Mare at ICAIP in 2009. The second edition was held in 2011, and this last one, which have been kindly hosted by the ICB Program Committee. Just to give you an overview of this competition is organized and structured in two parts. In the first one, competitors send us their algorithms in a form of an executable file, and these files represent the feature extractor and the classifiers, which are trained on a training set given by us. In the second part of the competition, which is called systems, the competitors sent us all their system, sensor, and the software they included into the package, in order to be attacked by the clever guys of our laboratories. So we assessed in this way the real performance that could be expected by these systems. In the case of the algorithm part, we prepared and collected 4 data sets made up each of 2,000 live and fake fingerprints, and used 3 optical sensors and a SWIPE sensor. The optical sensor were biometrica, ATAL data, and cross-match sensors, and finally a SWIPE sensor for data. The interesting, in my opinion, characteristic of this edition of the Fingerprint Liveness Detection Competition was that the first 2 data sets, biometric and ATAL data, were made up of latent prints. In the sense, we replicated the targeted client's fingerprints by non-consensual methodologies. In the second half of the competition, namely which use cross-match and SWIPE data set, we only tested according to the traditional way, by using consensual methodologies for replicating fingerprints. Finally, for the system part, we use consensual approach for replicating fingerprint and apply the replica directly to the sensor by separately assessing the error rates of the systems. With just 2 information about the spoof creation, when using the consensual or cooperative methods. What I show in this slide is just one of possible ways. This is maybe the best way, because we realize 3D replica of the fingerprint. This takes time, obviously, and the guy which is in charge of replicating the fingerprint must be clever in doing this, because the third stage of the fabrication step requires that each part of the mold, the material used for the mold, is in contact with the skin of the person. This is an example of a possible fake fingerprint we can provide by using this methodology. But we can also obtain entire finger-like spoof. If you take a look at the ICB spoofing challenge, my colleague maybe I'm show to you some impressive fake fingerprint with all the details exactly replicated by the material. With respect to the fake creation when using non-consensual method, we started on this edition, but we are planning to improve our methodology for the next edition, for the future possible edition of this competition, by using a simple piece of paper when the targeted client accidentally left his fingerprint. Then we use the standard powder used by forensic scientific office of the police to enhance this replica and to provide a print of this replica. This is the result, which is obtained by using a simple transparent foil for enhancing the difference between ridges and valleys of the fingerprints. Let's see the protocol of the competition. The protocol was very simple. The competitor sent us an exe file with a predefined set of parameters, and the main output of interest is the liveness score, a posterior probability of the pattern to be in the live class. As you may easily understand, the problem of liveness detection is simply a two-class classification problem when we have to assess the liveness or not of the pattern given as input to the classifier. As I said before, 4 data sets with 4,000 at least images for each of the data sets. We had in this edition 9 participants, 3 of them preferred to be anonymous. I can't give you any details about the algorithm they used for this competition because LDAO, they are free to send us some information about the algorithms used. None of them decided to do this. In this table, I summarized the results on 3 on the 4 data sets. We have biometric ital data in SWIPE sensor, and the average computed on these 3 data sets, being the 4 under study due to problems occurred during the competition. You can easily recognize the participants from the labels, but 3 of them are anonymous. Anyway, the winner, according to this 3 data set, is the algorithm presented by Dermalon. Just to see, even for sake of curiosity, which kind of information we can extract from this list of accuracies. More details you can find in the paper in the proceedings of this conference. I have plotted the results from LiveDet 2011 on the same 2 sensors we used in this edition, namely the Biometrica and the IDAL data sensors. And compared, even if it is not completely fair, this results with the non-consensual methodology used in this edition. We can see from this plot that even if appear to be relatively simple, recognize a latent fingerprint, the average results and standard deviation I reported in this plot suggested that it is not so trivial. We have an average of 90% of accuracy on overall accuracy between live and fake classes, but a standard deviation of 10%. This standard deviation is more or less the same we obtained in the previous edition, against an accuracy more or less about 70%. So, just to project in a possible future, when an attacker will be so clever to provide a better latent fingerprint, a fake fingerprint detector could be not enough powerful to face with this problem. And let's go to the second part of the competition, systems, the part systems. The protocol was more or less the same, with the difference that we asked to the competitor to send us all the package. These are the main results we obtained by attacking this system. It appears that attacking a complete package is more difficult, much more difficult than attacking a simple algorithm, let me pass the term, because we obtain very good results for the algorithm provided by all two participants. A problem that it is anyway to be discussed is the increase of the false rejection rate, which could be caused by this kind of systems. Anyway, we have to face with a clear impact when we decide to integrate these liveness detector systems on a fingerprint matching system. So, to conclude, the number of participants was encouraging because it's growing with respect to the previous editions. This means that the topic is worthy to be followed by the scientific community, and also the participation of several private partners assure that there is a general interest in this problem, besides its intrinsic scientific interest. Part 1 showed that we must be careful in deciding that fingerprint liveness detection is a solved problem. My personal opinion is this a very open problem that it is necessary to investigate in depth by, in particular, looking at the physical meaning of each feature which is used to perform a detection, liveness detection. In part 2, we provided more encouraging results, but anyway, in at least one case, we have noticed a high false rejection rate, which anyway could still be a problem when we decide to integrate this system to a real fingerprint matching system. And last but not least, I would like to thank all my colleagues and the colleagues of Stefan Schuckers, which cooperate with us in preparing this competition. And thanks for the time.
Any question? I know that everybody wants to know who are the anonymous people. I guess from industry, right?
Yeah.
Yes, of course. Other questions? No? So we can take advantage of the fact that there are no questions to move to the fifth presentation. So the presentation will be on iris recognition. So the title is the first ICB competition on iris recognition. And Okay, there is no paper together with this presentation, so pay attention, because you won't find these details anywhere. And the presentation will be given by Man San.
Good afternoon, everyone. Today I will introduce the first ICB competition on iris recognition. I'm Man Zhang from Cassia, China. Because we use large-scale iris image databases for training and testing, so we just finished our work in recent days. We will analyze all the submitted algorithms and publish a paper in the future. Today I will only show the computation results. As we know, captured iris images are highly different because of noise, illumination change, deformation, occlusions, and so on. So, unpredictable variance of iris images bring a great challenge to automatic iris recognition in real-world applications. So, the goal of the first ICB competition on iris recognition is to test the robustness of state-of-the-art iris recognition algorithms. In our competition, we use two data sets. The first one for training is Cassia Iris 1000 database captured by iris skin camera. There are totally 20,000 iris images from 1,000 subjects. And the second data set for testing was captured by iris guard camera. There are totally 10,000 iris images from 1,000 subjects. This table shows the detailed information of the 8 participants. They are all from different organizations and different countries. They came from Brazil, China, France, India, Japan, and Sweden. In the competition, each participant can maximally submit 3 algorithms, and the algorithm of best performance is selected for computation and ranking. In the competition, all possible intra-class comparisons are taken. So there are totally 20,000 intra-class matches. And 1 sample is selected from each class for inter-class comparisons. So there are totally 1,999,000 inter-class matches. And in the testing stage, if a comparison cannot be successfully implemented due to some reasons, such as failure to enrollment or failure to match, we will assign a random variable ranging from 0 to 1 as the matching score of 2 images. And at last, we ranked all the algorithms due to their FNMR value when FMR is equal to 0.01%. Due to our ranking rule, we found that the 7th, 8th, and 5th algorithms are the top 3 ones, and the first algorithm is still be tested. So we only show the testing results of other 7 algorithms. These are the score distributions. And these are FMR and FNMR graphs. Also, this table shows the information of the top 3 algorithms and their results and their developer information. Also, we draw the ROC curves of top 3 algorithms. Okay, at last, I must give my great appreciation to all the participants of the ICIR. Thank you for your efforts. And We can see that great progress has been achieved in iris recognition. However, great efforts are still needed for automatic pre-processing and matching of low-quality iris images in real-world applications. And in the future, we will analyze all the submitted algorithms and publish a paper about the competition. Thank you very much.
So any questions? Any questions? Yes.
Do you have information about which part of the problems come from segmentation and which part of the problems come from feature extraction and matching? Because in iris recognition, it's always interesting to see which part is the problematic one. So do you have any results on that, or do you only have the overall result?
Pardon, so sorry, I cannot,
So the question is,
I cannot understand it fully.
Yes, excuse me. The question is if you are able to understand from which side comes the problem, segmentation or matching, or you have any idea where the problems are? Segmentation is a problem? Segmentation. And or matching.
We're testing the segmentation and matching in the whole process, not separate. Yeah.
Any other question? No? So, okay, let's thank the speaker. So this ends this session. So we'd like to thank the speakers and the attendees, and also Sebastian for taking the burden to organize the competitions. So thank you once again. If there are no announcements from the organization, any announcement from the organization? Thanks once again.